Well, hello everybody. Welcome to another wonderful day of class. So today the plan is to go over the homework for the relations that we talked about last week. And if you have specific problems you want to go over, then please write them in there. Otherwise, I'll just start with the first one and keep going until we see how many we can get through today. All right. With that said, we're looking here, and this is the book. So the first problem we had was number 2. And what we had was A was the set 1, 2, 3, 4, 5, 6. And I wanted R to be the relation that is divides on A. So we would say A is related to B if A divides B. What I want to do is I want to actually illustrate this using a diagram instead of having to write out the set, because the set becomes cumbersome. But if we have a nice diagram, we can quickly refer to what this looks like. Alright, so let's go ahead and do that. In order to start this, what I'm going to do is just write out my set. 1, 2, 3, 4, 5, 6. So I'm going to have each of the elements represented by a point on my board. And I'm going to say, okay, 1, 2, 3, 4, 5, 6. Now, if A divides B, A is related to B. So if A divides B, then A is related to B. And so that means that the point, or the, ordered pair, AB, is in my relation R. And so those are the ways that we refer to these as either ARB or AB is in R. So if ARB or if AB is in R, the way we're going to do this pictorially is we're going to draw an arrow from A to B. So for example, we'll start with 1. 1 divides 1. Therefore, there should be an arrow from 1 to 1. So I'm actually just going to draw in a loop here and say I started at 1 and ended at 1, because 1 divides 1, so 1 R1. In the same way, 1 divides 2, 1 divides 3, so I'm drawing an arrow from 1 to 2, 1 to 3, 1 to 4, 1 to 5, and 1 to 6, because 1 divides all of these numbers. Then I'm going to keep working my way through. So I started with 1. What is 1 related to? Well, it's related to each of those. What is 2 related to? Well, 2 is related to itself. 2 does not divide 3, so I'm not going to draw an arrow there, but it does divide 4, and it does divide 6. So I'll draw an arrow from 2 to 4 and 2 to 6. If I look at 3, 3 divides itself, and 3 also divides 6. So I'm going to draw an arrow from 3 to 3 and 3 to 6. If I look at 4, 4 divides 4, but it doesn't divide anything else in this set. The same thing with 5, it divides itself but nothing else. And 6 divides itself but nothing else. So what we get is the relation divides, that is A is related to B if A divides B, would be pictorially represented by this. And so we could say, okay, if I start with this number, is there an arrow pointing to this number? That means 1 R6. 2 R4, but 2 does not R5 because there is no arrow there. And so it gives us a nice way to pictorially look at it, to visualize what's going on, and to quickly refer back so that we can tell if things are related. All right. The next problem we have here is 4, is we're going the opposite direction. We have this diagram, and what I want to know is what are my sets A, and what is my relation R. So here R is a relation on A, given by the diagram. Can we write this out as sets? So we want to make sure if we can go one way, we can also go the other way. So let's go ahead and do that. Now to find A, I'm just going to write the elements that are listed in my drawing. So A is just, now I have to look at this to make sure I get this right. That is 0, 1, 2, 3, 4, 5. So A consists of 0, 1, 2, 3, 4, 5. And so R is going to be the set of ordered pairs where of the form A comma B such that A is related to B. And so I'm just going to start with 0 and say, well, there is a line from 0 to 0, 0 to 4, and then that would be it. So we would have R has the ordered pair 0, 0, and 0, 4. If I then move on to 1, 1 is going to be related to 1 as well as 5 as well as 3. So we have an arrow from 1 to 1, an arrow from 1 to 3, and an arrow from 1 to 5. So R is going to consist of 1, 1, 1, 3, 1, 5. So again, I'm reading off and I'm just starting and saying, okay, 0 goes to 0, 0 goes to 4, so I'm putting those ordered pairs in. 1 has an arrow to 1, 1 has an arrow to 3, 1 has an arrow to 5. 2 has an arrow to 2. It also has an arrow to, well, now I have to look back. 2 also has an arrow to 4. So we'll have 2, 2, and 2, 4. And then we would move on to 3. 3 has an arrow to 3. And it also has an arrow to 1. And then we have 4 has an arrow to 4. It also has an arrow to 2 other places, to 0 and 2. And then lastly, we just have 5 to itself. And 5 also goes to, I believe, 1, although I should check the diagram. Yes, 5 goes to itself and 1. So what we get is the relation is a subset of A squared. So therefore it's ordered pairs. And we have the ordered pair if we have an arrow from the first entry to the second entry. So that would be our set R, or the relation that we're looking at. All right. All right. The next problem we had in there was number 6. So we said congruence module 5 is a relation on set A equals Z. And so we would say X is congruent to X, Y, Ry if X is congruent to Y mod 5. And so we've actually done this one, and we did this in detail on Wednesday and Friday. So I'll just refer you back to the other video, but we noticed that things are congruent mod 5 if you can write one as 5k plus the other, or that is if each of them can be written as 5k plus the same remainder r. And so we figured out what these would look like and how the different options we would have. So I'll let you look at those for those. And so that was the homework from section 11.1, and then we moved on to 11.2, which was 2, 10, 12, and 14. So I'll scroll down till I find that homework. All right. So now we have the relation R is given by the set of ordered pairs on A cross A, where my original set is A is A, B, C. What I want to know is this reflexive, is that symmetric, and is that transitive? So what this problem comes back to is just remembering what each of those things mean. What does reflexive mean? Well, reflexive means that every element is related to itself. That is, that A for each element in the set A. So I should they have A in here, so I should say XRX for each element in the set A. So all I'm going to do here is I'm going to look at these elements and say, can I find AA? Is AA in the set? No, it is not. Therefore, this is not a reflexive relation because there exists an element which is not related to itself. Notice that CC and BB are in here. So if AA was in here, it would indeed be reflexive. I have to make sure all of those are in there, but since one's missing, it is not a reflexive relation. What does symmetric mean? Well, it means that if XY is in there, then YX is in there. So we're just going to check these and say, well, I have AB, so I have to be able to go the other way. Is BA in the set? Well, if I look, there is no BA in the set. So again, this is not symmetric because A is related to B, but B is not related to A. If we continue, we can try the other ones and say A is related to C. C is not related to A. C is related to C. If you reverse that, you get the same thing, so we're okay. Same thing with BB. C is related to B, and B is related to C, so that doesn't fail the symmetric property. But the first two here we have do fail the symmetric property, so this is not symmetric, so it has to be true for all of them. All right, so if we want to see transitivity, what we have is if X is related to Y and Y is related to Z, we have to show that X is related to Z. So in this case, we have something like A is related to B, and B is related to B. Well, A is related to B. A is related to B, and B is related to C. Is A related to C? And so I'll actually go to the chalkboard and kind of write each one of these down. And I'm just going to go through each of the possibilities. There's a lot to run through, but I want to think, okay, well, what can happen? So I know that A is related to B. So I think, what are all the things B is related to? Is we have BB and BC. So if I combine these, I know A goes to B and B goes to B. So what I want to know is, combining these, does A go to B? That is, instead of using this one and this one, I go directly from here to the second part here. And notice that the element AB is indeed in the set. So this will be transitive for this one. But we can't just do it for one, we have to do it for all of them. So I do the next thing here, and instead of worrying about that one, I'm going to worry about the A goes to B and B goes to C. So again, I'm kind of removing this and say, does A go to C? And I do see that AC is in my set, so that's good. And then I have to try something else. Well, I've done all of the A ones, so now I'm going to start with B. And I get B goes to B and B goes to C. So if I go B to B and B to C, well, if I compose these two, what I get is BC in there? And yes, it is, because BC is right here. And since B is going to be here, it's just going to start at B and go to C. So clearly that's going to be correct, or it's going to satisfy the transitivity. So we're going to focus on the B goes to C, and I'm going to say, well, I know that C goes to C, and C goes to B, and I just want to see if anything else is in there. Nope, I have C going to C and C going to B, so I'm just going to ask, if I remove these, I end up with B, C. So I'm removing these, and I'm saying this is the first one, this is the second one. Is BC in the set? Yes, BC is in the set, so therefore we're still satisfying it. The next one I would have is to remove these two, and I would end up with, the question is BB in the set? And yes, BB is in the set, so we're still satisfying transitivity. So I started with A, I started with B. We're satisfying this transitivity thing so far. Next, I'm going to start with C. And for C, I have CC and CB. So if I look at CC and CB, that just says, is CB in there? Yes, it is. So then I can move on and say, well, what is B related to? Well, B is related to B, and B is related to C. So I'm going to start with this one, is I'll remove these two, and I'll get C goes to B. And notice that C goes to B is in there, so it's still satisfying transitivity. And if I look at the last two, I'm removing these two, and I get, is CC in there? Well, yes, CC is in there. And now I've checked all possibilities. I went through and tried to do this in a normal way so that I could keep track of everything that's happening. So I started with my A's and then my B's and then my C's. But if I do go through and brute force just check each of these, I get that each of these does satisfy the transitivity. So we get that this is a transitive relation. However, it was not reflexive and it was not symmetric because we found counterexamples. We checked all possibilities and found no counterexamples for transitivity, so it is indeed transitive. All right. The next problem we had for this section was number 10, I believe. I just want to make sure real quick. Yep, 10, 12, and 14. So number 10 says, suppose that A is non-empty. Since the empty set is a subset of A cross A, the set R equals the empty set is a relation on A. Is R reflexive? Is it symmetric? Is it transitive? If a property does not hold, say why. So let's just go through and say, same way here. If we have a set A, is the empty set reflexive? Means that for everything in A, it has to be related to itself. Now, the important part here is that A is not empty, so there's something in A. I don't know what it is, but I'm going to call it little a, just to say, then little a is in A or something. Because if it was empty, then there's nothing in here. I can't do this, but there is actually something in A since it's not empty. Now, is AA and R? Well, R in this case, they said was the empty set. This is a subset, this is an element in A cross A, and so this is not an element of the subset. So what we have is there exists something in A. That A in A cannot be related to itself because my relation is the empty set. Therefore, the relation of the empty set is not reflexive because anything in A is not related to itself. And because it's not equal to the empty set, there has to be something in A. Hence, it would not be a reflexive relation. I do want to point out if A was the empty set, so if A was the empty set, there would be nothing in A. So then we would ask, there's nothing to ask, so I don't have anything to ask here. And so technically by default, because it never fails, this would be reflexive. The empty set would be reflexive on the empty set. But on any non-empty set, it's going to be not reflexive because there is a question to ask. There is something A cross A. Is that in R? And the answer is going to be no because R is the empty set. All right, let's go back and say A is non-empty. Now the next thing we want to do is suppose A is related to B and B is related to C. We want to ask, is A related to C? So the point here is that this is an if-then statement. Now I'm trying to show that, I should actually write that out. I want to show that if this is true, then this is true. And so if this is true, then this is true. And if I want to prove that, remember that an if-then statement is only false if this is true and this is false. But if the if part's always false, then it doesn't matter what happens, this becomes always true. So that is, if I can show P is false, then I know that if P then Q is true. So now I'm trying to remind you of some logic, and we're really, this question just brings up a lot of technicalities. What is the formal definition? And we remember that if the P part, or if the if part is false, then the if P then Q has to be true, because it doesn't matter what happens with Q. We aren't saying anything. So an if then statement just isn't making any claim if the if part is false. All right, so why is that important here is there an A related to B in my set R? Is there a B related to C in my set R? And the answer is no. There are none of these. So what I'm getting here is that for the empty set, this is never true. So this is false since A comma B is not an element of the empty set, and B comma C is not an element of the empty set. Therefore, this part is always false, so the if then is always true. That is, there is nothing to check. There's no time where I actually have to make sure that it satisfies transitivity. There's no questions to ask or nothing to show. It's just, well, this can't happen, therefore the if then is true. So this would indeed be a symmetric relation, or transitive relation. So what I had up there was transitive, A to B and B to C implies A to C. Well, this part's false, so the whole thing's true, so it is transitive. On the other hand, if I wanted to show, symmetric, I'll write it down so I remember what I'm talking about. I have to show if this, then that. That should be an A here. So if I want to show if A is related to B, then B is related to A. Again, the if part is false, so it doesn't matter what happens with the then part. Because the if part is always false, there's nothing to check, so this whole thing becomes true. So therefore, the empty set would indeed be symmetric and transitive because there is nothing to check. The if part is always false, so the whole statement becomes true. So this is symmetric and transitive. It is not reflexive because there was something to check. There is something in A, therefore, that something in A had to be related to itself, but that was not in the empty set. So it is not reflexive because there is something to check, but it would be symmetric and transitive because there's nothing to check. I hope that makes sense and helps clear things up. If you guys have questions, let me know. Feel free to type in chat or speak in Discord. Whatever you need, just let me know. All right, the next ones we had were 12 and 14. So what we need to do is show that, or for number 12, it says, prove that the relation divides on the set of all integers is reflexive and transitive. Let's go ahead and do that one. So I want to show divides is reflexive and transitive. So I'm just going to remember I'm doing the divides relation. So A is related to B if A divides B. So if I want to show reflexive, I have to show that, let's use it because I have A's up there. I'm going to use X's. So I have to show X divides X for all X in my set Z. So in order to be reflexive, x has to be related to x for all x and z. So what I just have to show is that x divides x. Well, what does it mean for x to divide x is that x is equal to some integer times x. But notice that x is equal to 1 times x. So x is equal to some integer times x for all x and k and z, or for some k and z, but for all x and z. So therefore, x always divides x. So the division relation is indeed always reflexive. And that is my proof. It looks a little bare, but it's just saying, note, or we should say let x be in z. Then x is 1 times x, so x is an integer times x, hence x divides x for all x and z. Therefore, we are reflexive. All right, let's show transitive. So for transitive, what we want to do is we can say let x divide y and y divide z. We have to show then x divides z. So we get to assume that x is related to y and y is related to z, and I have to show x is related to z. And so if x divides y and y divides z, what do we do here is we start off with definitions. So x divides y if y is equal to x times some integer k1. Y divides z if z is equal to y times some other integer k2. And in order to show that x divides z, I have to show that z is equal to some integer k3 times x. So how do I do this is, well, I want to say z is equal to something is equal to eventually an integer times x. So what I notice is z is y times k2, but y is equal to x times k1. So instead of y, I substitute in x k1. But notice that this is just x times k1 times k2. So we let k3 equal k1 times k2. And we get z is indeed equal to this k3 times x. Therefore, x divides z. Therefore, this is indeed a transitive relation. So A divides B is a reflexive and transitive relation. All right. I do want to point out that it is not symmetric. So if we want to show it's not symmetric, we have to show the negation of the statement. But the original statement would be if A divides B, then B divides A. Well, I should use x's and y's. So if x divides y, then y divides x. So if this was true, this is the statement. That's what symmetric means. So if I want to show it's false, what do I have to do is I have to show somewhere where this is true and this is false. So I need to find an example of x divides y, but y does not divide x. Note this isn't too bad. We just have to say, note that 2 divides 4, but 4 does not divide 2. So we are not symmetric. So as opposed to having to work with this at all times, we just have to find one example, or one counterexample. And we can have, oh, 2 divides 4, but 4 does not divide 2. Or 1 divides 2, but 2 does not divide 1. Or 1 divides 3, but 3 does not divide 1. And so actually, the only way that if x divides y and y divides x is the only way that's possible is if x is equal to y. And so this would be non-symmetric. All right. The next thing we have here is that suppose that we have a symmetric and transitive relation, and there is an element A in which A is related to X for every X in A. What we want to do is prove that R is reflexive. I'm going to leave that one up to you guys to do so that we can move on to the next one. But the point here is you just let, say, y be an A. What we know then is A is related to y because A is related to everything. But since it's symmetric, y is also related to A. And then because it's transitive, y is related to A and A is related to y, hence y is related to y. So there's a quick walkthrough of what the proof there would look like. But you would get then that if we have A is related to X for every X in A, and we have symmetric and transitive, then we would also have to have reflexive. All right, so that's section 11.2. Now we can move on to 11.3, which is number 2, 6, and 8. All right. Oops, hit the wrong button there. All right, so in section 11.3, the first one we had was 2. So let's let A be the set A, B, C, D, E. Let's suppose that R is an equivalence relation on A, and R has 2 equivalence classes. We also know that ARD, BRC, and ERD, what I want to do is write out R as a set. All right. Now, actually, I'm going to do this one pictorially, and then I'll do it as a set, so that I can at least get it set up and know what's happening here. Is what we have is we have the set A, B, C, D, E. And if I want to think about what has to be related, is it tells me that this is an equivalence relation. There are 2 equivalence classes. And it also tells me that ARD and, sorry, I'm trying to look at the other ones we had, ARD and BRC. And ERD. So what we have is, to draw this out as a diagram, ARD, so we're going to draw an arrow from A to D, and we're going to draw an arrow from B to C, and then we're going to also draw an arrow from E to D, because E is related to D. Just making sure I have those correct. So that's what's given to me, is that this is going to be an equivalence relation, and it's going to have those properties, and we need 2 equivalence classes. So if I'm going to finish this up, what I need to do is say, well, let's walk through the properties. The first property of equivalence relation is that it's going to be reflexive. So that means x r x for all x in my set. So if I go through, I'm just going to finish filling in this diagram to make sure that this is true. So to be reflexive, I have to have this arrow as well. I have to have this arrow, this arrow, this arrow, and this arrow, because A has to be related to A, B has to be related to B, C has to be related to C, D has to be related to D, and E has to be related to E. So I'm filling in, or finishing the diagram, based on the fact that it needs to be reflexive. So I'm forcing that to happen. So I'm filling in these loops for A, B, C, D, E. Now the next thing I have to have is symmetric. So that means if A R or X R Y, then Y R X. So again, I'm going to fill in the diagram to make this true. So for example, ARD, so I must have that DRA, because it has to be symmetric. So because an arrow is going this direction, we also need an arrow going that direction. Again, because ERD, D also has to be related to E, so I have to draw an arrow in the other direction. If I do that here as well, I get BRC, so CRB. So therefore, I get that I have an arrow going that direction. Now, if I look at this just symmetrically, I've interchanged these arrows, I've interchanged these arrows. I also want to go back and make sure, am I still reflexive? So each time I do a new one, I'm going to check the old ones as well. So I've made this symmetric. Am I still reflexive? Yes, I am. So now my relation is reflexive and symmetric. And it satisfied those original three things they gave us. The next thing I want to do is say, is this transitive? So that is if x is related to y and y is related to z, then x is related to z. So I have to follow my arrows and I have to say if I can go from x to y and y to z, then I have to be able to go directly from x to z. So notice here that I can go from A to D and D to A, and I can also go directly from A to A. Great. But now I can go from A to D and D to E. Therefore, I have to be able to go from A to E. Now I can also go from E to D and D to A. So I also have to be able to go from E to A. Now, as far as transitivity goes here, I can go from B to C and C to B, and then obviously B to B and C to C, so that's transitive. If I can go from A to D to E, I can go directly from A to E. I can also go from A to E to D, but I can go directly from A to D, or vice versa. And so now if I look at this, this has become a transitive relation, because if I can go through any two steps to get to one, I could instead have gotten there through one step. So I now have a transitive relation. I want to go back. This is still reflexive. This is still symmetric because I can go both directions for any of these arrows. So this is a reflexive symmetric transitive relation. So this would be an equivalence relation. Now I do want to point out that we want to make sure how many equivalence classes are there. Well, if I find the equivalence class of A, that's everything that's related to A. And notice A is related to D, A is related to A is related to D, and A is related to E. Right now, that's it. So that would be the equivalence class of A, which would also be the equivalence class of D and E. And I would also have the equivalence class of B, consists of B and C. So notice that I have two distinct equivalence classes. So I've satisfied all the properties that they want me to. So this would be the equivalence class given by this problem. I do want to point out that can I add more is I could add more and still make this an equivalence relations, but I don't want to add any more because if I do add any more, I'm going to end up with something like E goes to C, but then C would go to E, D would go to C, C would go to D, and then basically what we'd end up with is one equivalence class because everything would be related to each other. But since we wanted two, we can't draw any arrows between these two sets. Therefore, this is what we'd have to end up with. Now, if you wanted to write that out as a full set R, since we have all the answers, the idea is just, okay, I have R, so I have to have A is A. A is also related to D, so I have to have AD and DA. A is related to E, so I have to have AE and EA. And I'm just going to walk my way through. And D is related to E, so I get DE and ED. So that would be the relations that I get from this set. And then I also have to get B is related. I forgot to put in, sorry. When I was doing D, I should also do D is related to D. And then I have to do E, so E is related to E. So I have A to A to D, A to E, D to A, and E to A. And then I have D to D, D to E, and I already had D to A. And then I have E to E, E to D was already up there, and E to A was already up there. So I have any pair using any of these two. So, which includes repetition. So I have all of these written down and pick two at a time, including repetition. And so these are all of the ways to do that. Next thing is to pick two at a time, including repetition for B and C. So I would get BB, BC, CB, and CC. So that would be my set R. And so what I've been able to do is I was able to draw a diagram. I was able to find my equivalence classes. And then from there, I was also able to write my equivalence relation as a set. And so that's what it's going to end up looking like. Depending on the context here, it was nice to have different ways to represent it. They asked specifically for this, that's why I did this one. But I might ask find the equivalence classes, or I might ask for the diagram. So you should be comfortable making all three, but you aren't necessarily going to have to make all three every single time we go through one of these. All right. Did everything make sense there? Does anybody have any questions before I move on? All right. All right, number 6 is there are 5 different equivalence relations on the set A. Describe them all, and a diagrams will suffice. All right. So now how am I going to do this one is I have to think about, well, what are all possibilities? I'm going to leave this one for you guys to actually work through on your own, as it takes a little bit of time, but you just think, well, if it's an equivalence relation, I have to have A related to A, I have to have B related to B, and C related to C. And in fact, there, you already have one. And then you ask, well, if I have A to B, I have to have B to A. And then that one would be an equivalence relation. But I could also have A to C and C to A, and B to C and C to B. Or I could have all three related in every direction. And so you just kind of walk through and say, well, what has to happen? If I draw in another line, what would then have to happen? If I had drawn in a different line, what would have to happen? And I can end up just finding all of the equivalence relations by going through that same process, basically as we did in number 2. We just then have to erase some lines and then start over and go through again and again until we find all of them. All right. The next one we had was number 8. So let's look at that. As we'll define a relation on R, a relation R on Z as x, R, Y, if and only if x squared plus y squared is even. We want to show that this is indeed an equivalence relation, and I want to define its equivalence classes. So I'm going to walk through these, but not necessarily write them all down. What I would have to show first is that it's reflexive, so x, R, x. What would that mean is, well, that means x squared plus x squared is even. Well, x squared plus x squared is 2x squared, therefore it's even, therefore x is related to x for all x in Z. There's reflexive. Symmetric. If x is related to y, then we know that x squared plus y squared is even, and we have to show y is related to x. So we have to show y squared plus x squared is even. However, x squared plus y squared is the same as y squared plus x squared. Since x squared plus y squared is even, y squared plus x squared has to be even. So I hope you guys write that down for yourselves. If you need to, you can go back over that. But the point is that we can commute addition for the real numbers. So we do end up with a symmetric relation. And the last one would be if x are y and y are z, then we know that x squared plus y squared is even, and y squared plus z squared is even. So what we have to show is that x squared plus z squared is even. Well, this one I might work with modular arithmetic, and I might say I know that x squared plus y squared is congruent to 0 mod 2, and I know that y squared plus z squared is congruent to 0 mod 2. Hence, if I take x squared plus y squared plus z squared, so I just add those together, I get x squared plus 2y squared plus z squared. But mod 2, this is y squared is just 2y squared is just congruent to 0. So I get x squared plus z squared. But x squared plus y squared is even, and y squared plus z squared is even. So if I add two even numbers, I add up with the even number. Or 0 plus 0 mod 2 is 0. So again, this will be transitive. Now, the thing about the classes is we just have to think about, well, what types of things would be related is, well, if I take an even squared, it's going to be even, and an even squared is even. Therefore, an even plus an even is even, so two even numbers would be related. If I take an odd squared, it's still odd, plus an odd squared is still odd, and odd plus odd is even. So every two odd numbers would be related, and every two even numbers would be related. This relation, or the equivalence classes, just becomes the odd, not e to odd, and even numbers. All right. As I said, I'll kind of let you work through that one too. You have kind of that talk through, but work through that for tonight so as you're doing the homework. All right, and the last one is section 11.4, number 2. So let's look at that one. Oops. Just trying to zoom in and then I left the page. So list all partitions on the set A equals A, B, C. Compare your answer to number 6 in 11.3. And you'll notice that as you did number 6, what you're going to end up with is relations, all of the relations. And if you find all the equivalence classes, each time you find one of those relations, you're going to find a partition, because every time you find an equivalence relation, the equivalence classes will form a partition. And every time you find a partition, it will be the equivalence classes for some equivalence relation. So if you did number 6, you're going to get that had you written out all the equivalence classes each time, those would then become all the possible partitions of A. So this one's going to actually be the same answer as section 11.3 number 6, which I had you guys working on your own anyway. So I'll do that and then compare your answers with what would the partitions look like. And remember, a partition is a collection of sets whose union is the whole thing and have no intersection. So one partition would be the set A and the set BC. Or the set A, the set B, the set C, or the set ABC. So again, I'll let you guys work on those. Otherwise, I hope wish you good luck on the homework. Make sure to get it done tonight and in by midnight so that I can give you credit for it. Otherwise, I will see you on Wednesday for some fun lecture on mappings. Thank you for joining me, guys. I really appreciate it. And I will see you Wednesday.